All right, so we'll stay in the realm of QCD this morning, and Adnan Bashir is going to tell us about continuum QCD approach to pattern physics.
Thank you very much. So I'll be talking about some of the hadronic observables using continuum QCD approach. I write the word here continuum just to emphasize that it's different from lattice QCD, which is the discretized version of QCD. It's basically it. So there are many complementary ways to go about. There are things that we learn from lattice QCD. There are limits that are harder to take in lattice QCD, like the chiral limit, which are easier to do in this continuum QCD approach that is done through Schwinger-Dyson equations and Bethe-Salpeter equations. However, the truncations that are involved in these schemes are harder to get a good handle on. So there are things to give and take in both these approaches, and there are times we get complementary results and get benefit from each other's research. Okay, so it's going to be, as it's going to be 1 hour, it's going to be an admixture between a seminar and a lecture. So some of the things I will present in slightly greater detail, especially the introduction, and some part a bit quicker, which are the results. Okay, so and I will, in fact, I can't focus on many things in this 1 hour, so I will be focusing more on a particular observable, mostly the form factors, electromagnetic form factors of two-particle bound states in QCD. Although I could present, there are results achieved for the form factors for nucleons transitions to excited states, the GPTs, the PDFs, etc. But I think it's a good idea to focus on smaller system to put across the way these things are calculated and arrived at the final results. So the two-particle bound states, as we know, have always been very important in physics. When you look at quantum electrodynamics, the simplest thing that you study when you're taking quantum mechanics courses after those hypothetical examples of a well and whatever, the first thing which has a direct physical relevance is the hydrogen atom. And the hydrogen atom is a two-particle bound state, and we know that lots of experiments that were done by Rutherford and its colleagues from 1910 to 1918 led to the discovery of the nucleus. And when Rutherford got his results, which differed from his supervisor, J.J. Thomson's idea of the atom, he communicated with his colleague, Niels Bohr, who came up with the atomic model called as the Bohr atomic model. So from their results, we had a lot of understanding of the spectrum of the hydrogen atom. And that understanding eventually led to the birth of quantum mechanics by Schrödinger. So after quantum mechanics, the experiments continued to study the spectrum, the transitions, which we would come to realize that also are very important in QCD. So one of the things that happened not very far from where we are today, there was a workshop on foundations of quantum mechanics in Shelter Island in 1947, where Willis Lamb presented his results on Lamb shift. So what he realized that there is a slight difference between the energy levels of 2s half and 2p half and the corresponding spectral line. And that's very small. That's only about micro electron volt. And we know that it's about 6 orders of magnitude smaller than the energies of the hydrogen atom. And at that point, it was not clear by theory how to explain it. And in that meeting, there were people like Feynman, Schwinger, and they were all very keen to try to understand how one would understand So this discrepancy, in fact, at that point led Dyson to say, if you do not understand the hydrogen atom, then you really do not understand anything. And then it all set into motion, the study of QED, quantum electrodynamics, at a deeper level. And that eventually led one to the understanding of what is called the renormalized quantum electrodynamics, the concept of renormalization, radiative corrections, calculation of Lamb shift, calculation of G minus 2, the anomalous magnetic moment of the muon, etc. So that sparked understanding two-body bound state and its excitation and spectrum led us to the deepest understanding of quantum electrodynamics. Now, what we know is that the simplest or the lightest two-body bound states in QCD or hadron physics are the pion and the kaon. So as I mentioned, it's two-body bound states, an equivalent of an hydrogen atom in QCD, and we expect that unraveling their internal structure is going to provide us, or it is providing us already, with a much deeper understanding of quantum chromodynamics. Now, these particles have a dual role. On one hand, they're the bound state of quark and an anti-quark, and on the other hand, they also Nambu-Goldstone boson, which are associated with dynamical chiral symmetry breaking, and that's a very interesting thing to compare and understand, because we have certain properties associated with these Nambu-Goldstone bosons. Now, we're still trying to understand pion and kaon. One of the things that will be done in the electron-ion collider would be to try to understand the electromagnetic form factors of both pion and kaon for large Q-squared transform, Q-squared momentum transfer by the photon, because we still do not understand it very well. We have the computation of it for very large Q-squared, which is asymptotic QCD result that we know from 1980s. And there are measurements done at the Jefferson Lab and earlier at CERN, which only give us information for Q-squared quite small. So this is one of the projects that will be done at EIC. And that is trying to know about pion, about which we know from a long time ago. As we already know that Yukawa was the one to predict in 1934 a particle called meson, which he thought was exchanged between a proton and neutron. That was after the work of Heisenberg, when he put proton and neutron in an isospin doublet. So he proposed the idea of 1934, and if you get to do some homework, we can try to do is to have a back of the envelope calculation using uncertainty principle, how one could estimate the mass of a meson, given that it's in a small volume of the size of a nucleus. So he got the Nobel Prize in 1949, a couple of years after the pion was discovered by Cecil Powell in 1947, who himself, for developing experimental techniques, got the Nobel Prize in 1950. Now, I was mentioning that these are Goldstone boson associated with dynamical chiral symmetry breaking. One of the papers that I've always very much liked to read was by Nambu, the article that he wrote in 1960. And if you read this article where he talks about chiral symmetry and chiral symmetry breaking and trying to understand why protons and neutrons are so heavy, 1,000 million electron volts, and he talks about in his abstract that he assumes that there is a fundamental field which obeys chiral symmetry, but then it is dynamically broken. And this breakdown is probably what is causing the proton to have a large mass. At that point, even the quarks were not mentioned. Gell-Mann's paper had not appeared, but Nambu was already considering the possibility of a fundamental field which breaks chiral symmetry, and gave his model in 1960. And in 2008, he shared the Nobel Prize with Kobayashi and Masukawa for his understanding for giving us the understanding of QCD. Now, about the structure of these. how do we understand the structure of hadrons? We have had very nice talks about the internal structure of hadrons. In particular, here we are talking about pion and kaon. One of the first experimental work, after Rutherford's experiment in which we were taking nucleon as a point particle, then Hofstadter started his experiments in early 1950s and tried to see the deviation of the results of considering the heavy nuclei as point particles, and that will tell us about roughly the size of these nuclei and what is the charge distribution. So those experiments was based upon elastic scattering, and he studied a multitude of nuclei, carbon, oxygen, etc., even hydrogen, helium, and tried to study and compute the radii of these particles, the charge distribution, and the Fourier transform of that, which are the form factors. So the form factors we now are the lowest moments of the generalized pattern distribution. So he did a lot of work on that, and he got a Nobel Prize also in 1960, 61 perhaps. Then, as we were having a very nice previous lecture by George, he explained to us in great detail the deep and elastic scattering concept, and that, of course, is breaking apart a proton. It's not an elastic scattering like you have in studying the form factor, in which you break this apart, and then there is a distinct scale involved. One is the large time scale, and which gets separated from the low time scale, and therefore you can treat here the partons as point particles with elastic scattering, and then we have the non-perturbative effects and the parton distribution functions. Those were studied in 1969. The idea of those proposed in the earlier article, for example, by Feynman. If you read Feynman's article, it's also a wonderful article. The abstract is just one-line abstract, introducing and understanding the idea of the distribution, longitudinal distribution functions for very high energy collisions. That's all what the abstract says. It's all about physics. It has no equation in it. Then, of course, I would not really talk much about the generalized parton distribution. That, in fact, so this here is just studying the internal structure of a proton, neutron, or any other hadron as a function of the longitudinal momentum fraction of the partons. Here you study in terms of the q squared of this photon momentum squared exchanged or given to this nucleus, and then you can have a combined analysis, and then you can also study as a function of forward momentum fraction xc, and you can study generalized parton distribution, which came about in 1990s, and with the work of not many people, you can have this deeply virtual Compton scattering. You can have meson production, which will give us ideas of GPDs in functions of q squared, in function of x, and as a function of xc. And from there, you can also reconstruct these quantities by appropriate integrations or limits that you want to understand. So when we understand, when we measure or do the experiments like EIC or Jefferson Lab to study the internal structure of these particles, what do we want to understand? Of course, what we want to understand is the underlying working or dynamics of the interaction that is giving the particle these structures. And that, in this case, is quantum chromodynamics. As I was telling you before, that understanding of the hydrogen atom led us to the understanding of quantum electrodynamics. We are hoping that understanding this three-dimensional structure or looking at different dimensions, component dimensions that we have of this three-dimensional structure, we would understand how QCD gives about this internal structure. What we know is that QCD in the infrared is characterized by two emergent phenomena. We have heard about these, confinement and also the generation of mass. when you look at the Lagrangian of QCD, it appears to be as harmless as that of quantum electrodynamics. The only thing is that instead of having U1 local gauge invariance, it has SU3 local gauge invariance. So you have quarks, you have three colors, and you demand the local gauge invariance, and that because instead of U1, it's an SU3, you have 8 exchange particles, 8 gluons in that joint representation. And then to include the dynamics of gluons themselves, you have to introduce it being a non-abelian theory. You have self-interactions of gluons, the interactions, and the 4 gluon interactions. So you can study it, of course, at the level of perturbation theory when the interaction strength is small, when we are probing the quarks at small distances or large momenta. But then, of course, there are phenomena which are non-perturbative intrinsically. What we know is that it does not matter, how much energetic collisions you do to produce lots of partons, lots of quarks and gluons, but much before they reach the detector, they conspire among themselves to form color singlet bound states. So this is what we understand from confinement, and these color singlet bound states can be mesons, baryons, tetraquarks, pentaquarks, or blue balls, etc. Now, on the other hand, I was also mentioning, like the questions that Nam was asking, why is that proton is so heavy? We understand from the standard model studying the Higgs mechanism and the discovery of the Higgs particle in 2012, which people expected all the time because that is the God particle which gives the masses to the fundamental particles. But what we understand is that in the Lagrangian, the current masses which appears for all the fundamental particles, especially in case of fermions, are free parameters. And for the quarks which are of interest for the world that we see around us, which is made of only up and down quarks, these masses are of the order of 3 MeV, 4 MeV, 5 MeV. And this is the mass which we understand is given to us by the Yukawa coupling that takes place between these quarks and the Higgs particle. So these 3 of these quarks, 2 up quarks and a down quark, sits inside a proton. When they traverse the distances of a head of the size of a Fermi, they acquire, or the dynamics of QCD gives the proton a large mass of about 1,000 MeV. So 3 particles of 3 MeV each at the Lagrangian level, giving a mass of a proton of about 1,000 MeV. Okay, so how do we try to understand that? So one of the ideas, of course, is as George was mentioning, it's the degrees of freedom which are important. We know that at the level of the Lagrangian, the degrees of freedom in QCD are the quarks and the gluons. If you're studying there in covariant gauges, you of course also make use of the ghosts. So how is it that you can start from these particles and then be able to understand how they're put together to study the structure that we want to study? So now it could be that the origins of both confinement and dynamical generation of this large mass of a proton can be traced back to the green functions of quarks and gluons. And I would actually, in a couple of slides, I will come back to what these green functions are, what are the equations of these green functions are, the propagator and the vertices, and how from there we can try to deduce some information about the generation of large mass. I would not probably talk a lot about how that is related to confinement and the mass balls, probably in the complex plane. But if there are any questions or interest, we can talk about it a little bit. So when we look at, for example, the quark propagator, I will come back to it. I just wanted to flash this transparency. If you look at the propagator in terms of the Feynman rule, it's like 1 over p/-m. But if you study it non-perturbatively, this 1 and m will be modified by some non-perturbative functions, because there are 2 functions which are required describe a spin half fermion. And one of these functions which sits where the mass is in the propagator is generally dubbed as the mass function. And if you're able to study these theories non-perturbatively under most suitable assumptions, you would see that this mass function, most of these theories are studied in the Landau gauge, runs as a function of momentum. This mass function being a function of momentum is equivalently saying that it is a function of the distance between the quarks in some sense. So it's just shown. I will come back to this graph much later. What I want to just say at this moment is this blue curve corresponds to the U and Lie quarks, and U and Lie's quarks in this large momentum where you basically have perturbation theory valid. This mass function corresponds to value of about a few MeVs, but when you study it non-perturbatively, then in the infrared, when the distances are large, this mass corresponds to a few hundred MeVs of this quarks, which more or less tells you that there is an effective rest mass of these quarks, which in a way explains to us why a proton instead of a few MeVs has a mass of a thousand MeVs. Now, this information comes from studying the propagators at the level of the Schwinger-Dyson equations, the non-perturbative propagators. Now, these emergent phenomena of QCD, which is both confinement and the generation of mass, these are in fact not existence in perturbation theory, and one expects that it is either linked either to one or both, is to the infrared enhancement of the strong coupling or the non-abelian nature of QCD, or in fact both of these. So the So the effects of this mass generation mechanism, which I have shown here, there is one curve which is shown also in this black, which tells us that if we had started with a Lagrangian which has quarks with zero mass, and even then, if you want to study it non-perturbatively, due to the large coupling involved here, the QCD generates its own scale in some manner, and even if there was no initial generation of the mass due to Higgs mechanism, there will be a large mass generation for these quarks in the chiral limit. So this can be associated with large coupling, and then one can from these, then you want to study the bound state. These can be 2-particle bound state or 3-particle bound state. That means you're studying either the Bethe-Salpeter equation or the Faraday equation. And then you study how the information that you had from these degrees of freedom, how would it translate to the degrees of freedom that describe your bound states. So what we will come eventually will be, say, for example, how the form factors are of these mesons and baryons. These form factors can be either elastic or electromagnetic form factors, or the transition form factors of a nucleon going, for example, to its excited states, like we studied hydrogen going from one state to its excited state, which led to the understanding of Lamb shift, etc. Okay, so one can try to roughly study how or if these things can be observed. Okay, let me come back for one moment to this. What we will see is that when we will do the computation, for example, of these form factors, you'll see that because the Bethe-Salpeter equation, these bound state equations, involve the study of the quark propagator other than the amplitudes or the interaction with the photon that comes in to observe it. These more or less run in a similar fashion. These form factors, you'll see that most of the times these are infrared enhanced, And then when the momenta are large, they make a transition to the perturbative or asymptotic limit in the case, say, for example, of electromagnetic form factor of pion and kaon. So there is non-perturbative scale involved in one side, and there is a perturbative scale involved on the other side. And what we'd like to see is if experiment can do the measurements in on both sides, and if there can be some theoretical predictions on both sides as well. Now, there is just this, how do you say, a bit like a cartoon picture, not a cartoon picture, but assuming that these states, which are pion or sigma, rho, or an A1, let's assume that they're only made of effective quark and an anti-quark degrees of freedom. So if that is the case, then, for example, pion being an isospin triplet and a pseudoscalar particle will be represented by this operator, and sigma would be a scalar particle represented by this operator, and then there is a vector and an axial vector. Now that's where they sit in the mass scale. If you look at the chiral transformations which are the transformations between right and left. So let's look at SU2 right and left transformations, which are equivalent to studying vector or axial vector transformations, because you can translate by taking a linear combination from one to the other kind of transformations. There you see, for example, that this axial vector transformation for a fermion or a quark field would look like this for SU2. And then if you study how a pion field will transform under these transformations, so you take the fermion field, do the transformation. This is one of the things that you can do, fill in the steps in your homework. And when you study, then you will see that this field, in fact, transformed to this plus this. And you look here, and this thing is basically what a sigma will look like if it were made of only quark and an anti-quark. That means that these chiral transformations or axial transformations rotate a pion to a sigma or vice versa. And similarly, if you do it on the fields which are rho and A1, you can see that the rho gets rotated into A1, or A1 gets rotated back into rho. So if these transformations were invariant, you would expect that the masses of the corresponding bound states will be the same, because they are preserving these transformations. These are a good symmetry. But when you look at it, you'll see that the difference of mass scale is between these sort of chiral partners is of a few hundred MeVs. The same is true of a few hundred MeVs between the massives and between rho and A1. And one can try to get an attention to this, that when we studied the effective generation of a dress mass for a quark mass was also the order of a few hundred MeVs, 300, 350 MeVs. Now here I haven't shown the structure. Something similar you can also observe if you study the nucleon and its excited state. The first excited state of nucleon, which is of opposite parity, is N star 1535, which is about 600 MeV heavier than the nucleon. In delta, it's the same delta. There's 1232, and the first opposite parity, same spin delta, is delta 1700, and that's about 5.5. So it could be that these things are related to each other. So how do we go about studying these, and how do we go about also studying the form factors? So I was telling you that I will be talking about Schwinger-Dyson equations, and I think probably many of you will not be familiar with what Schwinger-Dyson equations are and how do they work. So I'll just step back for a couple of slides to talk about what these are. So let's, for example, go to quantum electrodynamics for a moment. So this is how do you represent in perturbation theory a bare electron propagator. Now, if you look at what are the possible ways that virtual particles can be exchanged, George has been explaining it to us in great detail, these radiative corrections. This collection of diagrams was first looked at by Dyson in 1949, I think. So if you look at this electron propagator, of course, only interacting electromagnetically, it can emit a photon. it can absorb it, emit another one, absorb it, or it can emit in different ways. This photon can create electron-positron pairs, etc. Now, if you look at these diagrams a bit carefully, for example, I have collected here a certain kind of diagrams where, this, if you put this red circle here and then they squeeze the circle, you will say that all these corrections basically can be summed up as corrections which come in this internal propagator here. So what I mean to say is that all these type of corrections which are here, I can put a blob here which will contain, which doesn't interfere with the vertex or the photon propagator, can all be summed up here. If you look similarly to these kinds of correction, these kinds of correction correspond to this full blob here or the full photon propagator, where anything can happen to this photon propagator at any level of perturbation theory at any loop. And then there are corrections to the vertex. And those can be put all in a blob here. Now, in fact, then you can put them together. And when you put them together, what you can see is that the perturbative series can be summed up as all these possible corrections. And then these corrections can be repeated. That is to say that then there is a full propagator again, because this whole process can begin all over again. And if it begins all over again, then this propagator can again be written as all these corrections. So all this, in fact, if you define what we can call self-energy without this external propagators here, if you define it as the full self-energy, then you can write this series as the full electron propagator, which is the pair propagator plus this pair propagator. Then there is a self-energy sitting here, then there is a pair propagator here, and all these things get repeated. Okay. Now, it can be written in a compact form. What you can see is that if you look at this part of the series, then you can take this pair propagator and self-energy as common out, and then you can see that the rest of the series can be written as S0 plus S0 sigma S0, etc. So all this series, in fact, is nothing but the initial series itself. So if it is the initial series itself, then this can be represented by the full propagator, and you can write the equation like this. Now, this equation can also be inverted. You can multiply from the right side by S inverse P and from the left side by S0 inverse P, and therefore you can see it as written, and then you reorder it, and therefore you can write it in terms of inverse propagator as such. S inverse P is equal to S0 inverse minus the self-energy. So this is what is called either the Schwinger-Dyson equation for the electron propagator, which is the full Schwinger-Dyson equations between the propagators are non-perturbative in nature, and that is also sometimes called the gap equation. Similarly, you can go ahead and do the derivation of other propagators and vertices. I gave the example of QED because it is simpler, and you can do this diagrammatic approach. Dyson used this diagrammatic approach to write down the Schwinger-Dyson equations for quantum electrodynamics. This, what we saw in a bit greater detail, is the Schwinger-Dyson equation for the electron propagator, and this is for the photon propagator. This is for the 3-point electron photon vertex. And then you can, in fact, go on. You can see that this has a coupled structure. This is the 2-point green function, and that is related to this 3-point interaction vertex, which is there in QCD. Again, this 3-point interaction vertex appears in the description of the photon propagator. And when you talk about the full 3-point vertex, it is related to the 4-point. And then there is an equation for the 4-point vertex, and it continues. It continues this infinite set of equations. Now, it's not recommendable for a PhD project to try to solve coupled nonlinear integral equations which are infinite in number, because it requires usually infinite amount of time, and that's not so feasible. Now, there are good and bad things here. The good things is that is the following. Although here we had looked at a perturbative series, and then we subbed that as non-perturbative blobs, but when we talk about a perturbation theory, intrinsically we are saying is that a coupling is small, and therefore you can do a perturbative analysis. You can do a diagrammatic expansion. But then this was also derived by Schwinger later on, 2 years after the diagrammatic approach of Dyson. He did it from path integral formulation by taking functional derivative of the green functions, which do not require any recourse to the smallness or being large of the coupling constant. So the derivation of these equations do not require if the coupling is small or the coupling is large. So in fact, these can be equally studied for non-perturbative part of a field theory and the perturbative part of a field theory, if you could do that. But if you do a perturbative expansion, it becomes the XS matrix expansion that you have in normal quantum field theory. Okay, so people started trying to solve it. They were given in 1949, 51. And I would like to mention that one of the first articles written on this was by one of the founders of the Standard Model of Particle Physics, which was Abdul Salam, along with his student Robert Dilbergo. They wrote a few articles on it. And they started working in 1964. And then Robert Dilbergo kept working on it on this theory. One of the first articles they wrote was to try to look for solutions of these Schwinger-Dyson equations away from perturbation theory, and they did it in electrodynamics. Afterwards, Dilbergo also studied it for Standard Model and for QCD, but didn't do much after, say, 1980, and didn't study really so much the problem of chiral symmetry breaking in it. But their method of studying it was writing down the full propagator and the vertices in terms of what are called the spectral functions, and then try to solve for the spectral functions. So this work started a long time ago. Then there was a work by Vladimir Miransky and his collaborators. They imagined what happens if you're working in quantum electrodynamics, but you have a quantum electrodynamics which is, atomic quantum electrodynamics. We know that the coupling constant at the momentum scales that we probe quantum electrodynamics is about 1/137. At the Z boson mass scale, I think it's 1/128, but still it's very small. Well, what happens if you imagine a quantum electrodynamics where instead of 1/137, there will be a universe in which we have a large coupling? So what they found studying this Schwinger-Dyson equations techniques of solving the propagator equation is that when the coupling in quantum electrodynamics reaches of the order of 1, where you expect some non-perturbative features to set in, there is a new solution which emerges, and that solution bifurcates away from the perturbative solution. And even if you have an electron mass initially with 0 mass, then you'll see that electron generates a mass in quantum electrodynamics if it had a coupling which were large enough of the order where you expect perturbative things to set in. So that was an interesting observation. They also studied then a few years later QCD, in which they took some large effective average value of this large QCD coupling and studied the relation between the pseudoscalar meson in the ground state nonet of mesons. Then it was later also taken up by a group in Kent State University by Peter Tandy and his postdoc Peter Maris in 1999, and studied the same gap equation that was studied by Vladimir Miransky and some other groups earlier on. What they did was basically the same thing as I was talking about the quark propagator, that this is what we call the quark non-perturbative quark propagator. That quarks are spin half particles, and at the perturbative level, the Feynman rule is 1/p/-m. But because they are spin half particles, in the most general form, what you can write is that their propagator will be a function of two things which will depend upon the momentum square which flows. And one, of course, will be proportional to the gamma Dirac matrix, and one will be proportional simply to the non-existence of that. And that's only two constructions that you can do in parity conserving theories. Now, what they did was to make an answer. So the original work says that this is the kernel which appears here. So you can make an ansatz for the gluon propagator. In fact, for a product of a gluon propagator and the quark gluon vertex in such a way that your perturbative one loop result is reproduced for the gluon propagator and for the anomalous dimensions of the quark propagator. And then it has some parameter which gives you a large infrared scale. Of course, things have changed since then because you have a much better understanding of how the gluon propagator is through lattice QCD. You have a much better understanding is what the quark gluon vertex is, both through the continuum methods and lattice QCD as well, although lattice QCD can probe only some kinematic limits of this quark gluon vertex. But the result is what I was telling you here. So there is a quark, and even if it has zero mass in the Lagrangian, it generates a large mass. If you have an infrared enhancement, which will give you the correct, for example, you use it to fix it like the pion decay constant, and once you fix it, then it comes up. Okay, sorry. Oops. Now from there you can go on to study the bound states. Okay. So the bound states are spin 1 bound state and spin 0 bound state. They're pseudoscalars, scalars, vectors, axial vectors, and then you have 3-body bound states. For example, if you're studying a meson, in particular a pion, which is a pseudoscalar meson, in fact, whether it could be a pion, a K1, an eta C, an eta B, and eta primes, which are slightly differently handled because of the anomaly. So this is the equation in which a pion, which is this, made of a quark and an anti-quark, can have an exchange of all kinds of possibilities in this kernel, quarks and gluons of all different kinds being exchanged. Now, this is a Goldstone boson, and Goldstone boson have some particular relationship in which the beta salpeter amplitude, which come from a complete description of a pion, which requires 4 elements. This requires 4 elements, while the propagator requires only 2 elements. So this requires an information of the quark propagator here, the quark propagator, and any kernel which appears here. So you have to choose the kernel in such a way to make sure that your axial vector word identities are satisfied. And once you do it, what you see is that you can start with whatever you had obtained from the quark propagator, and from there you can compute your beta salpeter amplitudes, which are carrying the internal structure of your pion or a kaon and any pseudoscalar meson. So what is interesting to note is that whatever evolution of K comes about in the quark propagator more or less translate into the momentum evolution in the beta salpeter amplitudes. So you would see that when you do your perturbation theory, for example, for large Q squared, it goes as 1 over momentum squared. And for example, this E of Kp, it also goes up 1 over momentum squared. But if you had constructed or made some brute approximations in which your mass is simply a constant, you will see that your amplitudes are also constants. So somehow this momentum evolution of what happens here translate into the momentum evolution here, and eventually it goes into the momentum evolution of the form factors, which are measured in different laboratories. Now, as Osh was mentioning, that these quarks interact with photons. In fact, we are quite lucky that the quarks also have electromagnetic charge. So the structure of the bound state, like a proton or a neutron or a pion on kaon, owes itself to the dynamics of QCD. But because quarks have also electromagnetic charge, we can probe them with electromagnetic probes. So this is one of the things that one can do. For example, that's how you measure the electromagnetic form factor of a pion that has been done in Jefferson Lab, and it will be measured at EIC. So this photon, in fact, interacts with this quark because quarks have an electromagnetic charge. And therefore, because quarks go through different kind of momentum on their inside the meson, they can carry one large or small momentum, and therefore their masses can be different. You have to look at the structure of this vertex also non-perturbatively, because that is used in ensuring that you have your charge conservation at all points. Now, this being a vertex, there is a momentum for one fermion, ingoing fermion, there is outgoing fermion, and then because it has a Lorentz index, you can construct three vectors from this. And then you can also construct these four scalars. And you can put them together. And in fact, in general, this vertex can be written in terms of 12 helicity amplitudes or 12 form factors, you can say. If you look at the Feynman expansion of any diagram, you know that the Feynman rule for the vertex is only gamma mu in electrodynamics. But when you go to higher orders, you will see that all these structures come about. Okay? And in fact, when you're studying non-perturbative form of this vertex or correspondingly the quark-gluon vertex, all these structures play a certain role, and you will come to appreciate that that happens. Now, in fact, this vertex will also have its own equation, a Schwinger-Dyson equation that we can solve, and now actually people can solve it in some way. But what you can use is, in some ways, is that you can invoke many times an ansatz for this vertex, which is based upon gauge covariance relationship, its connection to perturbation theory when momenta are large, etc. Some of the gauge covariance relationships are Ward identities. But Ward identities fix a certain part of this vertex. Then there are transverse Takahashi identities given much later, which only look at the transverse part of this vertex. And then there are, of course, relations which are called Landau-Kalatnikov-Fradkin transformations, which are different from Ward identities, because Ward identities are something that relate, say, a two-point propagated to a three-point vertex, a certain endpoint green functions to an n+1 point green function, while the LTF transformations, they just look at one of the green functions and say, okay, if this green function has a certain value in one gauge, what it will look like in another gauge. Okay? So they don't necessarily, if you make sure that one is satisfied in a field theory, not necessary that the other one will be satisfied too. So in fact, using these identities and the implications of these transformation and renormalizability and connection with perturbation theory, then all these 12 structures either written in this way or in this convenient form, which differentiate the transverse part, which is transverse to the photon momentum, and the longitudinal part. You can have a lot of constraints coming on how you can understand on this vertex. Now, when you have a better handle on these vertices and the propagator, which come into the calculation of the propagator, the beta salpeter amplitude, and the vertex that is probing these internal structure, then you can go ahead to calculate your form factors. So this here is a triangle diagram in which the photon is talking to the quark inside and trying to compute the form factor from there. Now, understanding the form factor, as I was mentioning, has these elements. There is a quark propagator, which is here. There are three quark propagators here. Here, there is a bound state of upper Pauen, which means you are inserting here your beta salpeter amplitudes. And then you have this photon quark vertex. And I briefly mentioned about this to you. Now, I was telling you that there are good features of Schwinger-Dyson equation, there are bad features of that. And one of the bad features is that you have to make the truncations of these infinite set of equations. There's some point you have to just drop the rest of the equations, assuming that you know sufficient information for a particular green function using your symmetries of QCD. Okay, so that has its uncertainty. In perturbation theory, it's a controlled uncertainty. In non-perturbative truncation, it's not. So one of the works that was done by a postdoc in Mexico was trying to, there are several groups in the world which use these truncations and these methods to solve these and compute your form factors. What happens if you try to make different kinds of models, if you try to make different kinds of assumptions, if you try to different kinds of formalism to solve them numerically, how different those can be. But what one discovers is that once we have those models, their model parameters fixed to getting you the right pion decay constant and giving you, say, the right charge radius, then there is not a lot of freedom left. And what you see is that different variations give you the results of the pion form factor. Here we have drawn about 4 GeV squared to quite a precise value. I will not go into the discussion of distribution amplitudes because I think that I don't have a lot of time left, but the pion distribution amplitude for the valence quarks is quite consistent with our at the hadronic scale of 2 GeV is rather consistent with the computations which are done either through lattice or Schwinger-Dyson equations. But I'll not discuss that. So you can study this for the pion, and you can study similarly for the kaon. In 1990s, when the experiments were carried out at Jefferson Lab to compute this form factor, kaon form factor, they're all over the place. But they are now at the 12 GeV upgrade. They are doing an analysis of the kaon form factor up to about 5.5 GeV squared, and there are already preliminary results up to 5.5 GeV squared, and the error bars are a bit less. I hope I can come back to this. So why do we do this? So here it's from up till about 4 GeV squared, and this is somewhere where I think that, to my knowledge and the way we do it in our group, this is the best thing we can produce using these methods of continuum QCD, which we have the most precise knowledge of this. Now if we can do that, then what we see is that one aspect of using this is that we can probably test the precision of the standard model in some way. I was when I started talking about, I talked about the lamp shift. One of the observables, which is quite well sought after in standard model precision test, is the G-2 of the muon, the anomalous magnetic moment of the muon. And you will know that most of the uncertainties which come for the computation of these observables come from the uncertainties of QCD and hadron physics. And that has been a problem because theory has been unable to go beyond a certain uncertainty bars because our lack of understanding of how hadron physics will work. So I'll go through it quickly because that's not the idea of EIC and Jefferson Lab. You know that this is how you define the magnetic moment of a particle of spin S. Pauli and Schwinger already knew in 1927 through adding a term for the electron spin that it was a spin half particle, and then the Dirac equation of 1928 gave you this gyromagnetic ratio equal to 2, and any variation of this from G equal to 2, which will come from radiative corrections, corresponds to the anomalous magnetic moment, whether it is of electron or of a muon, and it is generally parameterized by this quantity. And that, of course, was this calculation was possible after the renormalization by Tomonaga, Schwinger, and Feynman. And Schwinger himself was the one who did the first computation of it in 1949 at the one loop level, giving us the result of alpha over 2 pi, which is, I think, 0.01166. The amplitude of a muon scattering of an external electromagnetic field is like this. And you can express not in terms of this 12 amplitudes that I had talked about, because the electron here and this electron are on shell. And once you put them in Dirac spinners, that you can expand in terms of what is called the Dirac form factor and the Pauli form factor. And in fact, this Pauli form factor for Q equal going to 0 is going to tell us what is the anomalous magnetic moment of these. So one can in fact do this computation, and I just want to briefly mention it that this QCD corrections that order corrections to anomalous magnetic moment of the muon come at alpha cube level, in which you have the possibility of, in this box diagram, a pion entering. So it's like a photon probing a pion, P+, so that's where the pion electromagnetic form factor computation is helpful to compute these quantities. So now that we understand it quite well, what we try to do is to calculate the contribution of these computations to the electromagnetic anomalous magnetic moment of the muon. And what we found that within the error bars are quite compatible with what you can find with dispersive method or lattice QCD. We also tried to compute the effect of the radial excitations of pion and kaon. That's not so much relevant. What is relevant for today's talk so much is the following. You know that every 7 years you have this long range plan of nuclear physics and particle physics and everything else in USA. In 2015 long range plan of nuclear physics, it was mentioned that the study of the pion electromagnetic form factor will be one of the flagship goals of, at that point, the 12 GeV upgrade of the Jefferson lab, in which possibly the QCD form factor can make a transition from the non-perturbative region from small momentum square to large momentum square. Okay, so in fact, the 12 GeV upgrade, the data that is being collected would be able to measure. You see, so far the data that we have only gives us the values of the form factor to this Q squared region. There are asymptotic QCD results known from the computation of by Brodsky and Lepage from early 1980s, which gave us around this value, and that is when the Q square scale is much larger than any other scale which is involved in this process. So this 12 GeV upgrade would be able to, there is an analysis done by their experimental group, and they'll be able to measure this till about 8 GeV square, and if lucky, to be able to measure it about 9 GeV square with this precision level, which is this with these blue diamonds here. Now, the electromagnetic form factor can be measured in the same upgrade till about 5 GeV square. Then last year I spent at Jefferson Lab, and when I reached there for my sabbatical, one of the first workshops that took place was on the possible potential of a 22 GeV upgrade at Jefferson Lab. And one of the analyses that they had carried out was telling that the pion form factor can possibly be measured at a future 22 GeV upgrade to about 15 GeV square, and the kaon form factor to about 10 GeV square. Now, of course, there will be nothing that will be able to beat what will be done at the electron-ion collider in this context. So that will be measurement of pion and kaon form factor. And if you look at the yellow reports which are there, you know, it always has a science question, and then you try to see what are the key measurements associated with it. So the question is, can we get quantitative guidance of the emergent pion mass, and the key measurement it mentioned there, what EIC will be able to measure would be up till 40 GeV squared. Now that's quite amazing. That means that you are trying to hit your pion with that much energy, and you're still hoping it wouldn't break, and it will give you the elastic collision. And the kaon form factor will be measured up till 20 GeV squared. So that's resumming what the future facilities can possibly do. This is the range of 12 GeV upgrade of Jefferson Lab. This is the potential 22 GeV upgrade, and these black ones are the future EIC measurements for the pion form factor. Okay, then you can of course go to study the three-dimensional structure of pion and kaon. Now, I had a few slides that one can study the GPDs of these particles as well, but I will skip this, and what I will try to mention is the following. Okay, I mentioned to you a bit about how these Schwinger-Dyson equations work and how do they not work, and what's the good part and what's the bad part. But I think that's the way I would like to mention it, and then flash some more results. When we study these things, one of the ways you can do is what I call the sophisticated truncations, which mean you can make a lot of elaborate truncations of your green functions using most of the symmetries that you can use, conditions from multiplicative renormalizability, conditions from all one loop calculations of the green functions when you reach your perturbative domain, etc. That becomes numerically quite demanding. And most of the things that we can claim to do it quite accurately is limited to the QCD green functions like the propagator itself or the gluon propagator or the quark propagator and some of the mesons like the pseudoscalar mesons and the vector mesons can be more or less done quite accurately. Then there is another limit what you can do. What you can do is complete brute force approximation of these, which only looks at the infrared properties of QCD and nothing else. Okay, and that is something like a contact interaction model or a Namu-Jonales linear model, in which you only look at a constant mass which is created in the infrared, which doesn't run with the momentum scale. Okay. Now, the good thing is that it's so simple that you can compute a lot of things with it. Okay. You can probably compute most of the observable static and dynamic for mesons and baryons, but it's running with momentum scale doesn't give you good results at all. So it's more or less valid in the infrared region. But for example, you can study the spectrum, the mass spectrum of baryons, light, heavy baryons, their excited states, and all these results are quite good within 5-10% of your experimental results. Now, lately, what we have tried to do is, if we can have a bargain between these two approaches, and what we call, and we have been working on it for the last few years, are called algebraic models. Now, what are those algebraic models? Can we somehow have the same sophisticated results which come from the exact or QCD akin truncations, but are not so difficult to deal with as compared to the simplest models? Is that possible? So what we realized that when you calculate most of the physical observable, that computation come from lots of different products of propagators and amplitudes and the vertices. So what you try to do is you try to shift your Q-squared dependence from one entity to the other entity, but when you put them together, it's still the same. For example, you take a quark propagator, it goes as 1 over p square for large p square, but I put it as a constant. But if this momentum flows into the beta salpeter amplitude, okay, but the beta salpeter amplitude, I give that power to the beta salpeter amplitude. It doesn't change the physics, but it simplifies my computation a great deal. So what you try to see is, can you construct models like this to simplify your computation, but not at the sake of losing a lot of physics? So here, I'm already, my time is up for 1 hour. So we tried to construct somehow this one of the models. I'll not go into model. So there is a model for the beta salpeter amplitude rather than computing it in terms of subspectral function. And then there is a model for the quark propagator for the knowledge of QCD that we already have. And then you plug in and then you do the computations. You can do the GPDs as well. You can calculate the PDFs. You can take the limit and you can calculate the form factors, etc. But I'll not go into the GPDs calculation and the PDF results and the PDA results. But what I want to mention is that once you have this model that you think quite closely mimics your QCD and also has the simplicity, that allows you to go to larger Q squared for computing your form factors. And that was what we wanted to achieve with that. Now you can do it through two methods. Because the model is simple, you can construct your GPDs, and from there you can integrate over your X, and then you can compute your form factor, or you can compute the form factor directly from the triangle diagram. You can do both the things, and you eventually basically arrive at the same results. So in the beginning, what we do is that this is the algebraic model results, which are these blue bands. They have more error, more bars, because we give a lot of freedom to the parameters that one can choose, and they not behave so differently from the more exact calculation that we have done for pseudoscalar meson up till this 4GB squared. So they more or less are within the same error bars. But what you can do is that then you can go to higher Q squared. Okay, that the simplicity of the model allows you to do it. So what we do is that we could manage to calculate the prime form factor to basically as large a Q squared as possible using this algebraic model. And what we have, this blue band, which is coming from this algebraic model calculation. Here I would mention that there are lots of groups here in this place, like in Brookhaven National Laboratory. Last month, there were the lattice results that came for the pion electromagnetic form factor up till about 10 GeV squared, or for the kaon up till about 28 GeV squared. That's the result from their group that I have just only recently put there. Interestingly, we put the paper out the same day that they put for the lattice, so we didn't have that in the paper. But so these green bands are coming from the lattice calculation from the group of BNL. This algebraic form factor results are our results, and these are for large Q square, the ones that will be probed at EIC. So that's for the pion, and that for the kaon. I was telling you that there is currently being data analyzed at JLab for the kaon form factor, and this is the preliminary result of this experiment. This courtesy Garth Uber, who provided us. When we did this computation, we didn't have these results, so we didn't use that in any way in our analysis. But when you put this here, this is of course not quite okay with this blue band that we have for our algebraic model results, which we have shown here up till about 8 GeV square, along with these results from lattice that have just recently come out for kaon. We have shown here only about 8 GeV square, but these lattice results, for example, are available till 28 GeV square because the strange quark mass is heavier, so it's easier to do the lattice computation. So that's basically where I would like to stop. There is some, of course, summary and outlook, which only telling you, summarizing what we have done, some other things that we can do with it. The only thing that I will probably like to mention is that from the very first slide, that when I mentioned that it's important to study the simplest bound states because that give you the information of the underlying field theory, I looked at the simplest two-body bound state, which are pion and kaon, quark anti-quark bound states. But you know, most of the mass of the atom comes from the protons and neutrons, and the protons and neutrons are three-body bound states. So there are some work that we are trying to do in that direction. For example, this class 12 experiment is looking at the internal structure of the proton and neutron and its transition to its excited states. So one of the things that they try to measure are the transition form factors of a proton going to its excited states. Okay, so these are this is something that we are looking at. The only thing is that three-body bound states are a lot difficult as compared to two-body bound states. So we are looking at it to start with very simple models which have not have a very close connection to QCD, only in the infrared. But once we have a better handle of how it works, we will apply better truncations of Schwinger-Dyson equations to carry out the same study. So that's where I'll stop. And thank you very much for your.
Sorry, how do you excite the nucleons?
Sorry?
How do you excite the nucleons?
It's the same. It's a photon. You know, either it is coming from an electron emitting a photon, and that photon talks to the nucleon. It goes nucleon to say an n star state, n star 1535, which is the parity partner, and then it decays to the other states. Or you can have photon beams which do the same thing as well.
Yeah, because I was just curious how you do that at JLab with class 12, for example.
That's electroproduction. So it's electron-proton collisions, an electron emits a photon, and that photon is the one which excites the nucleon. So it can go to, you know, they are measuring it. You can excite it to deltas, for example, the different kinds of deltas. You can do to n stars. So they had the results. Those results are not known for very large values of Q squared. I think the initial results are only about 2 GeV squared. That's not entirely so helpful because that's the region where you have a lot of meson cloud effect, and that these, there are many theories which are not easy to handle that meson cloud effect, but this 12 GeV upgrade is allowing them to go up till about 4 GeV squared, and that's so there are some velocity amplitudes or the transition form factors available for some of the particles, like for delta 1600, delta 1700, also for n star 1520 and star 1535, and therefore, because I was there last year, they asked that we should do some computation for that to be able to see that. So one of my students is working on those transition. But again, for example, within this scheme, the way we do it, we don't study it as 3 particle bound state. We study it as a quark diquark structure, and use that to study these transition from fixed status.
I have simple question. I may miss that for diagrams in your model, there is no disconnected diagram, right?
Well, it depends upon which green function that you're looking at. So you have 2 particle reducible, connected, disconnected diagrams, depending upon which green function that you're in and how they are derived.
So, let's say that you said, I mean, these are perturbative techniques. So let's say that you want to study the PDF or TMDs. That you said that you can't do that, right? In principle.
This is the perturbative technique. This is
No.
yeah.
No, but it's like if you calculate those things, are that do you calculate them at just one scale, or can you just infer also the evolution? I'm asking
Yeah.
because these objects depend also on the scheme.
Yeah.
So which scheme would it be?
Of course. The thing is that most of the computation that is done for the propagators or the amplitudes, where it's repeated amplitude, are all done at a hadronic scale of about 2 GeV. For example, if you're looking at PDFs, if you look at the measurements that have been done, are not done at the 2 GeV scale. They're done, say, I think now at about 5.5 GeV squared. So you have to carry out an evolution of the results to reach that. Now, that evolution, so how do you go about doing that evolution? So one of the ways which is done is using the DGLAB equation, but the DGLAB equation, for example, it's a perturbative evolution equation. So what is done is that you use the one loop DGLAB equations, and the way most of the groups do is that you have that, but the only thing you make it non-perturbative. That is, of course, that is where the modeling comes, is the running coupling. So you take the running coupling from the non-perturbative knowledge, but other than that, the DGLAB equations are just one loop. And then you see how do those PDFs which you evaluated at 2 GeV squared evolve at 5.5 GeV squared, and then try to make connection with the experiment.
What it's not clear to me is how do you decide which scheme to use? Because in perturbation theory, we can decide whatever, but I mean, a non-perturbative, what do you use DGLAB? The DGLAB kernel in the MS bar scheme, say, as opposed to any other.
Yes, that's also it's also there will be ambiguities coming from the scale that the user type of renormalization do. Most of the time, it's the MS bar scheme, which is used even in the propagator evaluation, in the clone propagator, the quark propagator, and then you do the same. But yes, there can be ambiguities coming from this, and there can also be ambiguities coming from the gauge part. But all of this one is all done in the lab. There are some studies, I was telling you, there is some interesting work that I was involved in when I started my PhD thesis. that was on Shinga-Dyson equations, but nothing to do with phenomenology. It was trying to understand how the gauge transformations work. How do we make sure that when you calculate some observable through this method, how do you make sure that your physical observables are gauge independent? So one of the things that we started working on along with Michael Pennington was these gauge transformations, which are given by Landau and Kalashnikov and Fredkin. So they studied QED and they said, okay, if the electron propagator is like this in one gauge, then these are non-perturbative transformation. Then they will tell you how it will be in another gauge. Okay? Now, what you see is that here, when we do the truncation, what we see is that you study your Landau gauge calculation. You do one thing, you do another thing, and you make your approximation in one gauge, and that you stay in that gauge, you live your life in that gauge. So what happens if you want to do another gauge? But then we're working on it for the first time in QCD right at this minute. And we find interesting things is that what you do is that what you have to transform is that each green function that you're using in this computation has to be gauge transformed into the, well, that's a complicated business to do. So if you don't do it correctly, then you can't expect to get the right result. Well, what you can do is that once you have computed your quark propagator, you have the quark propagator, and you have the wave function denormalization, you have the mass function. And what does it look? Can you do that? Take a quark propagator and then transform it to other gauges and see how it looks like. Okay? And for example, one of the things you expect to be gauge invariant is the chiral quark condensate. Gauge independent or not, and the studies that we are currently doing is that tells you that is the case. So it's an exciting thing, but that's only for that. To be able to see that for things like form factor and other, it's I don't think I would have the time, effort, and courage to do that in the future.
Let's thank Adnan for we have 1 hour and a half for lunch, and we'll take the school photo after Yulia's lecture, after the first lecture, after the afternoon. Go outside. Take a photo.
Couple of things to think about this evening. We have the pleasure of a wonderful Indian dinner over in Port Jefferson. So the good news is we almost have enough cars to get people over there, but not quite enough to get people back. So I'll be looking for people. If you want to hang around in Port Jeff, there are trains back at 8 o'clock and 9:30. So think about that. And in the afternoon, I'll set up signups because it's sort of tight for cars, but we have most of them. There's a 5 o'clock train over there. We may need a couple people to ride the train over. We'll figure that out. So think about it. If you want to stay around in Port Jeff afterwards, that would be great. We need 8 to 10 volunteers to do that. And then we'll figure out cars afterwards. So have a good lunch. We'll see you back at 1:30 and enjoy.